Hi everyone, my name's Jeff Gamelli. I'm the Deputy Superintendent for the Water Resource Recovery Division, Department of Public Works, City of Westfield, Massachusetts. Today I'm going to video a tour of our treatment facility. You can see it right there, City of Westfield Water Pollution Control Plant. And here's our main gate coming in, power automated. Here to the right is our septic receiving area. So in the busy season, we'll take sometimes 30,000 gallons per day of septage from the hill towns, surrounding areas, and City of Westfield. Approximately half of the city is on septic systems and half are on sewer. So we get a good deal of septic in the busy season. 2 slots here for 2 trucks at a time. The septic dumps into these, we accept it based off of pH, and it dumps in and comes in through the influent. And our influent line runs underground, about 30 feet below ground, under the dumpster into the main building there. Okay, here we're going to enter the headworks of the treatment plant, where all the influent wastewater flows into the facility 30 feet below ground. We're designed to treat 6.1 million gallons per day, and our average flow is about 3 million gallons per day. Alright, so we're going to head down the stairs here. Those 2 devices right there are automated bar rack removal systems that remove the rags and any debris out of the wastewater that's a 1/4 inch in size or bigger. So it really helps remove all inorganic material, large objects, rags, all the material that you don't want in the rest of the treatment plant. So now we're at the bottom level of the treatment plant, and here's the 2 bar screens.
So this pushes and compacts. We'll go up the chute and then falls into the hopper. And it's basically a rag log.
These carts, we roll these carts over here to this hoist. We hoist the carts up to the top, and out the top door and dump it into the dumpster. Here you can see the apparatus, the monorail that the cart rides on from the hoist, and we dump our rags into this dumpster. So we remove about 2 carts of rags per day on average. So this dumpster will be full in a couple days of removing rags out of the influent wastewater. Okay, here we are in the influent pump room. This is the very bottom level of the treatment plant. On the other side of that wall are the influent wet wells. So we have 4 influent pumps powered by electric motors up above that are pumping the wastewater, lifting it from this level and pumping it up 30 feet to the aerated grit chambers. We have 4 pumps that will pump the peak design flow of 17 million gallons per day, but on average we always have 1 pump running. 1 pump can pump about 5.5 million gallons per day at 100%. Here we are 1 floor above the influent pumps, and here are the 4 electric motors that are powering the influent pumps. And these electric motors are 75 horsepower motors. Over here is where the influent wastewater is being lifted through this magnetic flow meter. This is the device that's measuring our flow. And our flow current is 4.66 million gallons per day. This magnetic flow meter is measuring the flow. Here's where the influent wastewater is exiting the building, headed to the grit chambers. Okay, here is the entrance to the plant. Here's the operations building. I'm walking out back. Those two tanks with those steel structures are the two aerated grit chambers. Wastewater is being pumped and lifted up to these two tanks where the grit settles out. And to settle the grit, the purpose of that is to protect all the downstream pumping equipment and piping and devices so it doesn't wear the equipment out, to eliminate abrasion through the rest of the plant. Now we are on top of the aerated grit chamber, and the purpose of aerating is to help the solids, the grit and sand and inorganic material, to settle to the bottom. And it gives it a vortex motion, lets it settle to the bottom, and flows out by gravity at this point through the rest of the plant. From here to the end of the plant, gravity flows unless the river comes up to a certain level, and then we need to pump it into the river. Here is a clamshell bucket, a grit hoist. So once a year, we remove the grit out of these grit chambers. We'll drain the tank, dig out the grit, load it into a waste management dumpster that'll be sitting here, and it goes to a landfill. So the wastewater, influent wastewater, is flowing from these aerated grit chambers to this distribution box. This distribution box divides the flow equally amongst the 3 separate treatment trains. And a treatment train consists of a primary clarifier, an aeration tank, which is considered secondary treatment, and at the end is the secondary clarifiers. Here's another primary clarifier, and so forth. Right there is our blower sludge building. It houses our sludge storage tanks. It houses our aeration blowers and a lot of sludge pumping equipment and thickening equipment called gravity belt thickeners. And here's our emergency generator fuel storage tank, 4,000 gallon storage tank of diesel fuel to operate in power outages. So here's a primary clarifier, and the point of the primary clarifier is to settle settleable solids and to float grease and scum. So here we are, it's flowing over the weirs. This is called primary effluent. This is a circular clarifier, and this arm goes around the perimeter and skims off the scum and grease into the scum trough located over there, which then gets pumped to our sludge storage system and is removed. At the bottom, we have settable solids, mostly organic material. Like I said earlier, the grit chambers collected the inorganics, but there are residual inorganics that flow to this side. And the sludge is pumped from the bottom, called primary sludge, and it's pumped to the sludge storage tanks. This primary effluent right here, this water, still has a lot of organic material, soluble solids, and total suspended solids, a lot of biochemical oxygen demand, and nutrients such as ammonia, total nitrogen, nitrates, phosphorus, and metals. Most of the metals should settle in this primary clarifier. This water then flows to the aeration tanks, where the activated sludge lives and breaks down the organic material in this water. So again, here's another angle of the primary clarifier. We're on top of the gallery. This is where the water is collected in these launders over these V-notch weirs and to the outlet pipe. At this point, this water is now considered primary effluent, leaving the primary clarifier. There's a scum collection trough. There's another primary clarifier, train number 2. This is train number 1. The old part of the plant, originally built in 1972, when the Clean Water Act was initiated and put in place. Here in this tank is the aeration tanks, where approximately 20,000 pounds of bugs, what we call bugs, activated sludge, microorganisms and bacteria break down the organics and the nutrients in the wastewater, cleansing the water to a very clean standard. And we follow NPDES, National Pollution Discharge Elimination System permit, and we're only allowed to discharge a certain amount of BOD, total suspended solids, and certain nutrients such as phosphorus and ammonia, and we have a threshold that we need to be under. So these bugs, the activated sludge, are working 24/7, consuming the organics and nutrients and taking in oxygen. So that's why we call it aeration tanks, and we're pumping approximately 1,000 cubic feet per minute of air into each one of these tanks. Primary clarifier is approximately 280,000 gallons, and this aeration tank is almost 600,000 gallons. So this is the influent side of the aeration tank. Flows by plug flow through these 3 passes and out the effluent side of the aeration tank onto the secondary clarifiers for stratification and settling of the activated sludge. And here's treatment train number 2 on this side. Each train can handle about 2 million gallons per day average design flow. And this piping here is the aeration piping, where all the forced compressed air is pushed into the aeration tanks to feed the bugs oxygen. Just like any animal, they need food and they need oxygen to live and consume the food and the water and reproduce, and they die, they have a life cycle. So in